So, what we learned so far? Let us recall that. We start talking about mathematical statements. We said that suppose P, Q, R, and the rest of them are mathematical statements. We introduced some connectors or operators to define compound statements. Compound or more complicated statements. For example, we have the negation of a statement. Then we had and. We also defined or. We defined conditional statement and also biconditional statement. We saw truth tables for each of them. And we also learned about some important laws connecting these statements together. Very well. So what is important about P, then Q? It was equivalent to not P or Q. Now I expect you to ask, what if I want to find the negation of P then Q? The negation of P then Q is not P then not Q. To find the negation of P then Q, they have to convert that into not P or Q, then use De Morgan's law to distribute the negation. To find the negation of a conditional statement, for example, P then Q, we are following this. We say that, hey, not P then Q, first needs to be written as not P or Q. This is a very first step. P then Q, not P or Q. Then we use De Morgan's law. To distribute the negation over parentheses. So here we have the negation of not P, the negation of or, and the negation of Q. What do we get? We get not P, and not Q. We also learned about double negation rule. Double negation, which says not P is the same as P. We have and, not Q. So the negation of P then Q is P and not Q. P and not Q. Important relation for you. In chapter 3, we're going to talk about quantified statements, existence, and universal quantifiers. So let us begin by a general question. This question says, think about this equation. X squared is greater than equals to 0. So we saw this inequality many times. X squared is greater than equal to 0. It means that if I square a number, it's always greater than equal to 0. Very well. We all know that this statement is always true. Statement is always true. No matter what x you choose, if you square it, it's going to be always greater than equal to 0. Now, how about this one? Another question. X plus 1 equal to 0. You have a linear equation and you say that, hey, is this equation true for all numbers, for every random number that I choose? Of course not. This equation has exactly one solution. The solution is x equals to -1. In logic, there's a difference between these two statements. In logic, we can use a universal quantifier for this statement. X squared is always greater than equal to 0, and an existential quantifier for x plus 1 equals to 0. So that's the main difference between these two statements. It's true for all numbers. This is true if there exists one value that satisfies this equation. So I'm going to write these side by side. Definition of a universal statement and the definition of existential statement. Existential statement. Okay. Let P of x be a statement. If it is true for every x in the domain, then we write for all x, comma, P of x. We read it this way. For all. Let's add the domain as well to make sure you know that you're working with the domain. If you change the domain, you might not get the correct answer. Belongs to the domain, comma, P of x. So for any x value number in the domain, P of x is a statement that's satisfying for that x. So this is called a universal quantifier. Upside down, capital A is universal quantifier. existential statement, let Q of X be a statement. If there is one element in the domain, if there is or there exists one element, like X in the domain, such that Q of X satisfies that X, you're right. There is flipped capital E, there is X in the domain. You can at least find one X in the domain such that Q of X. There is at least one member. Element, a value, a member in the domain such that Q of X. So this flipped capital E is existential quantifier. Perfect. Perfect. So let us talk about truth set. So let's define a predicate, and then we talked about the truth set. Well, when it comes to logic, we're interested in specifying statements that include some or finite variables. A predicate is a sentence with finite numbers of variables. So what do I mean by that? Consider P of...
Professor, can you please manually focus the camera? Yeah.
So consider P of X. P is a statement including independent variable X. So this is a predicate with only one variable. Like what? Like X plus 1 equal to 0. You might have two independent variables. Why not? Q of X and Y. We can just use this. Q of X and Y, which is a predicate with two variables. Like what? X squared plus Y squared equals to 1. So a truth set for a predicate. Suppose we have a predicate with domain D. For example, if you look at this predicate in one variable with domain D, we assume that the domain is all real values, all numbers. Then the truth set of the predicate is a set including all values, all numbers that make the predicate a true statement. A true statement. For example, for these two, we can define the truth set. For the first predicate, the truth set includes just one element, -1. The only value that makes this equality a true statement is -1. If I plug in -1 on the left-hand side, I get 0 equal to 0, even though the domain is R. What about the second predicate? What values satisfy this equation? The domain is R, Cartesian product with R, or your plane, XY plane. But what is the truth set? All values that are satisfying this equation. You can write it this way: the set of all x values such that y is equal to plus minus square root of 1 minus x squared, or you can write it this way: the set of all x values such that x squared plus y squared satisfying this equation. For example, 1 and 0 is a member, 0 and 1, -1, 0, 0, -1, and the rest of the values. More examples on the truth set. Next example says, suppose your predicate P of x be x squared is greater than x. The domain is R, all real numbers, and then it says, write P2. What is P of 2? What is P of a half? What is P of -1/2? And finally, it says, which one is true, which one is false? This is this example here. So, P of 2, it means that we just need to write down 2 squared greater than 2, or 4 is greater than 2, which is obviously true. A half squared is greater than a half, or a fourth is greater than a half, which is false. Negative a half. So here you have -1/2 to the power 2 is greater than -1/2, or a fourth. A positive number is greater than a negative number, which is true. Another example for you. This example says, let Qn be a predicate which is given as n is a factor of 8. Find the truth set if the domains are changing. The first domain is n belongs to non-negative, non-zero integers, or n, natural numbers. B, if n belongs to z, sign numbers. Okay. So factors of 8. Okay, in this case, the truth set can be 1, 2, 4, and 8. All of these are factors of I change the domain to be all signed numbers? In this case, the truth set includes positive and negative numbers, plus minus 1, plus minus 2, plus minus 4, and plus minus 8. On the next page, we're going to connect these quantifiers with connectors or operators in logic. So a universal quantifier, for all, for any, for every, is connected to the conjunction. Conjunction or and. And also an existential quantifier.
Professor, it needs to be manually focused again.
An existential quantifier, flipped E, is connected to the disjunction. Disjunction or. That makes sense. When you're talking about a universal quantifier, it is true for every member in that set. Every one of them. If you take each of them, it must satisfy in the statement. But when it comes to existential quantifier, we need at least one. So either the first one, or the second one, or the third one, and so on. So it's connected to or. Example for you. This example says, investigate the truth and falsity of these universal statements. True or false. The first one says, hey, the domain is given as 1, 2, 3, 4, 5. And consider this universal statement saying that for all x in the domain D, we have the following. X squared is greater than equals to x. Is this true or is this false? And the second one says, consider the following statements. For all x in R, for every element in real set, x squared is greater than equals to x. So what is our approach here? Since the domain is given to us, so since we have the domain and it is a universal quantifier, we have to check for each member. Again, here we have the domain. Domain is given to us. This is your domain. And also you have a universal quantifier. It means that it must satisfy for each of the members in the domain. Okay, so if I plug in 1, I have this. 1 squared is greater than 1, and it is true. If I plug in 2, I get 2 squared greater than equals to 2, which is true. 3, the same for 3, to the power 2. If I plug in 4, it's of course true. 4 squared is greater than equals to 4. And if I plug in 5, is greater than equals to 5. So it satisfies for each of these members in the domain. So we're happy. This is true. True statement. Well, how about this one? This is true for every real number. I'm going to give you a counter example. We can find a counter example for this universal statement. What's the counter example? Take a half. If x is equal to a half, a fourth is greater than or equal to a half? No, false. So you say that since I found a counterexample, it means that this universal statement is not a true statement. Since we found a counter example, it means that this statement is not true. This statement is not true. So this is for universal statement. If the domain is given to you, you have to check each member. If the domain is very vast, try your best to find a counterexample. Later on, we're going to learn methods of proofs to actually prove these types of statements. So I expect you to ask, what if we have existential statements? True or false? The first one says, there exists at least one member in positive integers or just natural numbers such that m squared is equal to n. B, let the domain be given to you as 5, 6, 7, and 8. And the statement says there exists at least one member in E such that m squared is n. Okay. Which one is true? Which one is false? This guy says, I can find at least one member. Just one member is enough for me, such that this equality is true. Well, can I find one number that satisfies this equation? Of course. So since it is an existential statement, one element, one member is enough. Can you find that one member? Of course. M, for example, is equal to 1. M equals to 1 is our answer. So this is true. What about this one? It says, hey, your domain is 5, 6, 7, 8. Can you find one member, at least one member, in between these elements that satisfy this equation? So take a look at this. If I plug in 5, it says, hey, 25 is 5. Of course not. So not the first number. What about the second number? 36 is equal to 6. 49 is equal to 7. 8. 64 is equal to. So as you can see, since the domain is given to us, we cannot find at least one member. None of these members are the solution here. So it's not true. So in general, to translate a universal quantifier, the wording that we use are for all, for every, any, it includes everything. And when you have existential quantifier, the translation is there is one, there exists. These are the translation. Or if you have there is one, there exists in a sentence, and you want to translate that into a logical form, you're going to use the flipped E or existential quantifier. If you have an example which says, hey, for all, for every, for any in general, you're going to convert that into a universal quantifier. For example, suppose we have the following. The first one says, hey, you have these statements. You have a universal quantifier, x belongs to R, comma, x squared is greater than equal to 0. They don't care if it's true or false. They're just trying to translate these. B, you have a universal quantifier, x is in R, and we have the following. X squared is not negative 1. And C says you have existential quantifier, M is a positive integer such that M squared is equal to M. So the possible translations, if you want to translate these, the possible translation can be written this way. You can say, so it's not translation. You might say, hey, any real number has positive or 0 square. Any real number has a positive or 0 square. This is one of the possible translations. B, any real number, its square is not negative 1. for any real number, its square is not negative. And C can be translated this way. There is one positive integer such that its square is equal to itself. There is, or we can find, one positive integer that its square is the same as the number. These are all possible translations. You might say, hey, how to translate it differently. As long as you're following the keywords, you're fine. Now we have some sentences. How do we translate them into logical form? For example, suppose it's given as all triangles have 3 sides. All triangles have 3 sides. Or you might have something like this. No dogs have wings. No dogs have wings. Or some programs are structured. Structured. Well, what are the possible translations? Okay. First of all, remember that when you're translating using quantifiers, remember to have the domain as well. So for any x in D, such that px, for any, there is, let's just write it this way, there is, for example, y in D, such that q of y for the rest of it. So don't forget to mention the domain. All, because of all, we're going to use a universal quantifier. All, or all, for any. Triangles, there we go. I need to define a domain includes all triangles. So I'm going to define the domain this way. Let T be the set of all triangles. Triangles. So T is going to be just one triangle, representing one triangle. So you can write it this way. You can say that, hey, for any T in the domain T, T has 3 sides. What about B? Here you have no dogs. It means that if I take any dog, that dog doesn't have wings. So P, let D be the set denoting all dogs. The set of all dogs. And suppose D is just one dog, representing one dog. You can write it this way. For any D in the set D, for all D in D, D has no wings. How about C? Some programs. There is one or more programs that are structured. So think about it this way. Suppose P is the set of all programs, and P representing one of these programs. One program. You can write it this way. There is there's at least one P belongs to P such that P is structured. Well, let's make it more interesting. Here's a question for you. These are the questions that I have. The first question is, what quantifier you use for Px, then Qx? What quantifier do you use here? Another question for you. What's the negation for all x in D, Px? What's the negation? There is x in D, Qx. So, what do you think, guys? How do you answer these questions? Write your answer in the chat. When you have conditional statement, the quantifier that we use is for all, for every, for any. For all x in D, if we have Px, then we have Qx. In this case, the truth set of predicate Px is included in the truth set of Qx. So for any x in the domain, if Px is true, then Qx. The truth set of the first predicate needs to be a subset of the second predicate. For example, suppose we have these statements. Let Qn denotes that n is a factor of 8. N is a factor of 8. And you have R of n, which says, well, n is a factor of 4. N is a factor of 4. Which one is true? Qn implies Rn, or Rn implies Qn? Okay. What's the truth set for the first predicate? N is a factor of 8. Remember that when you are using n, it means that you're working with natural numbers. So the truth set is 1, 2, 4, 8, and n is a factor of 4, it means that the truth set is 1, 2, 4. Which set is a subset of the other set? As you can see, for predicate Rn, the set is smaller than the truth set for predicate Qn. So Rn implies Q. One, 2, 4 is a subset of 1, 2, 4, 8. Well, let us move on to the next part. So, what would be the negation of for all? The negation of for all is going to be there exists. So, there exists X in the domain, X in the domain such that you have to negate the predicate as well, not PRX. And here, the negation of there exists is for all X in D, X in the domain, and the negation of your predicate, not that predicate, not Q. Well, now I expect you to ask, what about the negation of implication? Question. What is the negation of implication? P, then Q. B, what about converse? What about inverse? What about contrapositive? What do we do here? So, what do we do? Here we have implication. Implication means, hey, we have for any X in D, Px, then Qx. Well, to find the negation, you have to negate the whole thing. So here you have the negation of for all X in D, Px, then Qx, which is written as not Px or Qx. So we're going to use 4. When we distribute the negation, we get there is X in D such that not P. It means that our first predicate is here, the negation of or is and not the second predicate. Second predicate. So what if we have converse? When you have converse and you want to negate the converse, this is going to be the negation of for all X in D such that So remember that if we have P then Q, its converse is Q then P. So we're negating this one. Let me erase this one off the board. I need more space. Which is the negation of, we have to convert the implication using OR for any x in D not QX or PX, which can be written as there is at least one element in the domain such that not Q or just QX or converts into and not P. Not P. Inverse. So the inverse of the conditional statement is, in parentheses, we can write it as for all x in D. Here we have not P, then not Q. Again, to find the negation, we have to convert implication into OR, then use De Morgan's law. So this is equivalent, saying that, hey, we have not for any x in D, comma, so not P, which is PX, or not QX, which is equivalent, saying that there is x in D such that not PX and QX. Okay. There you go. And finally, the contrapositive, it's going to be the negation of, for any x in D, comma, so the contrapositive is not Q, then not P. And this is equivalent, saying that we have the negation of there is. So let us just write down the universal quantifier, then we convert that for all x in D, comma, so not Q, which is QX, or not PX, then we distribute the negation because there is x in D such that the negation of QX, not Q, not that Q is, and the negation of OR is going to be and, not P, gives you P and. So let's write this one. That's, here we go. The negation of all the definitions related to implication. Examples. Well, this example says, write formal or informal contrapositive, converse, and inverse of the following. So let me write this here, this one, contrapositive. So if you have P then Q, it is not Q then not P, and then write converse. You have Q then P, and write the inverse of the following. You have not P, then not Q. So what is the statement? The statement says if a real number is greater than 2, if a real number is greater than 2, so this is our hypothesis, then its square is greater than 4. Then its square is greater than 4. So what do we have here? This is your P, and this is your Q. What's the contrapositive? Not Q, then not P. So you can say that if square of a number is not greater than 4, so if the square of a number is not greater than 4, then that number is not greater than 2. That number is not greater than 2. So this is our contrapositive. Converse, Q, then P. If square of a number is greater than 4, then that number is greater than 2. So if the square of a number is greater than 4, then that number is greater than 2. Guys, we don't care if it's true or false. We're just trying to write the converse, inverse, contrapositive of a conditional statement. And finally, the inverse. Not P, then not Q. If a real number is not greater than 2, then its square is not greater than 4. If a number, a real number, is not greater than 2, then its square is not greater than 4. Different order, different meaning. Using not as a negation, it changes the statement. So you should be very careful when you translate a statement, when you try to negate it. Is it a conditional statement? Is it converse? Is it inverse? Is it contrapositive? Each one has a different meaning. So in this example, we are working with multiple quantifiers. What do I mean by that? Let's remember the definition of a reciprocal. Recall that. Recall it. The reciprocal of a real number like A of a number. Like A.
Professor, it needs to be merely focused. Oh, it's better now. Yeah.
Is a real number, B, such that A times B is equal to 1. Take a look at this example. Translate into logical statements. Well, let's see what we have. The first one says, every non-zero real number has a reciprocal. Real number has a reciprocal. This is your first sentence. The second one says, there is a real number with no reciprocal. There is a real number with no reciprocal. Well, what's the difference between these two? How do we translate them into logical statements? So let's begin by A. It says every. It means that any, every, for all, for any, a universal quantifier. For any non-zero real number. Non-zero real number, so take A. Take A to be a non-zero real number. It has a reciprocal. What's the meaning of that? It means that has a reciprocal, it means that there exists at least one. So there is B such that A times B is equal to 1. So for any real number, non-zero real number, there is a real number like B such that their product is equal to 1. What about the second one? It says there is a real number that has no reciprocal. So there is, of course, it starts with there is. There is a real number, like there is a real number like C. There is a real number like C. It has no reciprocal. If I take any real number, if I take any real number like D, this equality is not met. There is a real number that for any other number like D, this equality is not met. So be careful about the order, which one comes first, and the meaning of those quantifiers in the statement. So we are using multiple quantifiers in one statement.